Hey guys, this is Marco with Students Teach Orgo. Today we're going to be covering two topics again. First, we'll start with acetals, and then later on we're going to do carboxylic acid derivatives, so be sure to stick around for that. All right, so starting off, what's an acetal? So an acetal is basically any molecule that has two OR groups connected to the same carbon. So if we look at this one here, we have this middle carbon, and this carbon has two separate OR groups connected to it. So this is an example of an acetal. Hemiacetals are, I guess you could say, a subgroup of acetals where one of the OR groups is an alcohol. So again, we have our acetal looking thing here. We have this carbon with two OR groups, and one of the R's on one of the OR groups is a hydrogen, making this an alcohol. So that's a hemiacetal. All right, so just to get a little bit of practice identifying acetals and hemiacetals, go ahead and pause the video, see if you know what these are, and unpause when you're ready. Okay, so starting with this one on the left here, this molecule, as we see, has this carbon here with two OR groups attached to it, right? These are two separate O's, and each of these O's is bound to another carbon or an R group, right? So this here on the left is an acetal. This second one here, we see that this carbon is bound to two separate oxygens, right? But it's doubly bonded to one of the oxygens. So this is neither an acetal nor a hemiacetal. Acetals have single bonds to two separate oxygens. This third one, we have this carbon in the middle that's bound to two different OR groups. So this is an acetal. And then finally, this one all the way on the right, this carbon here at the top of the ring is bound to an OR group and an alcohol, an OH group. So this one is the only hemiacetal here. So hopefully that's all clear to you guys. All right, so cyclic hemiacetals. When we have a molecule that has an aldehyde or ketone, so a carbonyl group, and an alcohol that are spaced 4 to 6 carbon apart, that molecule can react with itself and form what we call a cyclic hemiacetal, which, as the name implies, is a hemiacetal that has a ring in it. Now, the mechanism for this, which we'll go into in depth on the next slide, follows the kind of skeleton mechanism I like to call the Pated mechanism. So each of those letters stands for a different step in the mechanism. So P is our first step, and it's protonation. A is a attack, a nucleophilic attack. T is a proton transfer. E is an elimination. And D is a deprotonation. Now for cyclic hemiacetals, you'll notice that the T and E steps have this asterisk here. That's because they don't always occur in cyclic hemiacetal formation specifically, but in other mechanisms that follow the kind of Pated skeleton, that they may or may not occur. So we'll get into that on the next slide. So on the left here, we have our precursor molecule, and you'll see it has a carbonyl group and an alcohol spaced 1, 2, 3, 4 carbons apart. All right, so this molecule, just by looking at it, we can see that it's going to form a cyclic hemiacetal. So now let's follow the Pated method for cyclic hemiacetals to get our product. So starting off with our P, our protonation, the first thing that's going to happen is this oxygen here, so the carbonyl oxygen, is going to get protonated by reacting with some kind of acid, right? And the purpose of that is to make this carbon here, right, this carbon here, sufficiently positive, right, to have enough positive character to have this alcohol now perform the A step, the attack, right? So if this we make this carbon more electrophilic, then this alcohol, right, which is a relatively weak nucleophile, can attack the carbon and begin to form our ring, right? So if we're forming a bond between this carbon here, which we'll label carbon number 1, and the alcohol group, that means the alcohol and then carbons 1, 2, 3, 4 are all going to be connected to each other in a ring, right? Which you can see in our next step here. So just to illustrate which of these carbons corresponds to which one in the ring, this carbon here, the one that we're attacking, carbon 1, corresponds to this carbon right here, which you'll see now what was initially the ketone, or the aldehyde, I'm sorry, what was initially the aldehyde becomes an alcohol, and carbon 2, 3, 4 are part of the ring, and then finally this O that's in the ring was the alcohol that we initially had. So after our attack step, the alcohol still has the proton attached to it, so we need our deprotonation step to get rid of that positive formal charge on that oxygen. And then that's our final step and leaves us with our cyclic hemiacetal, right? Which, looking at this molecule, you'll see that this is in fact a cyclic hemiacetal. We have this carbon here bound to an OR group, right, which is part of a ring, and to an alcohol. So this is a hemiacetal. Now, very closely related to cyclic hemiacetals are cyclic acetals. The difference here is that instead of having a ketone and an alcohol 4 to 6 carbons apart, we have an acetal or hemiacetal and an alcohol 4 to 6 carbons apart. And again, similar to the cyclic hemiacetals, this follows the Pated mechanism, but this time the elimination step is required. So we have, in this case, PA, maybe T, E, and D. So let's look at that more in depth. So here is our precursor molecule on the left. You'll see that we have this acetal here, right? This carbon is bound to 2 separate OR groups, and that is spaced 1, 2, 3, 4, 5 carbons apart from an oxygen, or from a alcohol group, right? So just looking at this, we know that this is going to undergo some cyclization reaction to form a cyclic acetal. So again, following Pated, our first step is P, protonation. So we will protonate one of the acetal alcohols, giving us this, right? And similar to last time, that makes this carbon sufficiently electrophilic and allows this relatively weak alcohol nucleophile to attack the carbon, right? So now we're forming a bond between this carbon, so carbon 1, which I labeled, and the alcohol here, and carbons 1, 2, 3, 4, and 5, and this oxygen are all going to be in the ring, right? So now we have a 6-membered ring. Now, in order to make this attack step occur, right, if we want to form a bond between this oxygen and this carbon, we need to break one of the bonds that this carbon already has, right? Looking at this intermediate, this carbon already has 4 bonds, right? One here, one here, one here, and one here. So in order to form another bond, we need to break one of these existing bonds because carbon can only have up to 4 bonds. In order to do that, we kick off this methanol group that we just made, right? And that's our elimination step. So by protonating this oxygen here, initially, we make this entire OR group sufficiently stable as a leaving group, which allows us to break this bond pretty easily and allow this O to form a bond to what it was initially our acetal carbon. Okay, so I hope that's clear. So after the cyclization, right, we still have an H attached to what was initially our alcohol, right? This oxygen here was initially our alcohol oxygen. So to remove the formal charge there, we just have to deprotonate. And after that, we're left with our cyclic acetal. And you can indeed see that this is a cyclic acetal. We have this carbon right here and 2 separate OR groups bound to it. Okay, so for protecting groups, we in organic chemistry sometimes want to, as we say, protect carbonyl groups from certain kinds of reagents. Like say we have some kind of precursor molecule that has, say, a carboxylic acid on it and a carbonyl group that have pretty similar reactivities when reacting them with reducing agents or Grignard reagents or organolithiums, for example, right? So if we want to preserve the ketone but react the carboxylic acid, we need to, as we say, protect the carbonyl group, which we do using ethylene glycol, this molecule right here. Now, the benefits of using ethylene glycol is it takes the carbonyl group and converts it to a cyclic acetal, as you see here. And then at the end of the reaction, when we want to convert the carbonyl back into the carbonyl, it's very easy to do. We just react it with some acid, and it reverts from this to this. We'll go into a mechanism in depth on the next slide. But the purpose of the protecting group is to, as we say, protect the carbonyl from reagents that we don't want it reacting with, basically. And again, just to clarify, this only works with aldehydes and ketones and not with esters and carboxylic acids. So let's look at the mechanism for this. As you might be able to guess, if this is a cyclic acetal formation, the mechanism is going to be very similar to the pated mechanism. So we begin by protonating the carbonyl oxygen up here, right? And again, that makes this carbon down here, so this carbon, sufficiently electrophilic, and one of the alcohols on our ethylene glycol can attack that carbon, right, and convert what was initially a carbonyl group into an alcohol, right? So this right here corresponds to this. So here we have a protonation step followed by an attack. And then after our attack, we need, this is where the proton transfer step comes in, right? Finally, we're using T in the pated mechanism. So one thing I want to mention here is I showed this as two separate steps, right? First, a deprotonation from this oxygen, and then a protonation on this oxygen. Some professors prefer you showing this in two steps. Other professors are okay with you doing this in one step and drawing this arrow and this arrow in the same step. I personally would draw out the two steps because I'd rather be safe than sorry. But if your professor's okay with you doing just one step, then that's fine. But make sure before you do anything on the exam. Anyway, so then we have our proton transfer step, right, which I drew out as 2. So it's just the hydrogen here bouncing from this oxygen to this oxygen. And in doing that, right, we convert this, which was initially our carbonyl oxygen, into a very good leaving group, right? Water is a very stable molecule, as I hope you know by now, so that can just pop off as a leaving group very easily. And that is facilitated by a lone pair from this oxygen dropping down to the acetal carbon here. And in doing that, we form this kind of almost like a ketone looking thing, which allows us to take this second alcohol on ethylene glycol and attack that carbon again, right, to form our second C to O bond that's necessary for the cyclic acetal. So after that step, we're left with this. And then finally, we just have a deprotonation. Again, that's always going to be our last step. So this hydrogen pops off as H+, and we're left with this molecule right here. Now, for the reverse reaction, it's basically this mechanism, but in reverse. So you would start with this and then react with acid and go this way down the mechanism to revert back to your ketone. So just keep that in mind. Okay, let's get into some practice problems now. Go ahead and pause the video and then come back when you're ready. Okay, so looking at our precursor molecule here, we have a ketone on the left-hand side here and a carboxylic acid on the right-hand side. Excuse me. And I see that our first step involves ethylene glycol, right? So that should tell you right away I'm protecting the carbonyl group. Now, again, remember, it's important to note that the ethylene glycol will only react with the carbonyl group here and not with the carboxylic acid group here, right? Don't get that mixed up. So our first step is going to change this into our cyclic acetal, like that. And again, this is to protect the carbonyl group, and as you'll see later, this is going to come off and restore our ketone later. Next, we're reacting with lithium aluminum hydride. So you should know from the last video that will reduce our carboxylic acid to a primary alcohol. So let's go ahead and do that. All right, we basically just delete this doubly bonded oxygen and leave an alcohol group. And now we're reacting with some aqueous acid. This is a step in which our cyclic acetal will now come off and form our ketone again. And then finally, we are reacting with some acid. Looking at this molecule, we see that we have our carbonyl group and an alcohol spaced 1, 2, 3, 4 carbons apart. So that should tell you I'm forming a cyclic hemiacetal. And if we go through the mechanism for that, we get this. Oh, and I numbered the carbons just to make it easier for you to see, but we get this as our final product here. If you need some help getting from this to this, I encourage you to rewind and watch the cyclic hemiacetal again. Okay, practice problem 3. Go ahead and try this one. Okay, so we have this molecule here, which we see has a aldehyde and 2 alcohol groups. And each of the alcohol groups is 1, 2, 3, 4, and 1, 2, 3, 4 carbons away from this aldehyde group here, and we're reacting with acid. So again, this should tell you that we're forming a cyclic hemiacetal. Following PATED, right, our first step is protonation. So we will protonate that aldehyde oxygen. And now it doesn't really matter which alcohol we choose to attack first. We just start with the one on the left in this example. So that alcohol will attack as our A step. And that forms our first first ring here, our first cyclic hemiacetal. And of course we need the deprotonation step. And we end up getting this. Right, now we can use the H plus that comes off in this step to catalyze the next step in the reaction. So that will protonate this oxygen up here and give us a good leaving group, right? And you'll see now we have this this acetal here, or hemiacetal here, and an alcohol that are 1, 2, 3, 4 carbons apart, and that should tell you, well, now I'm going to form a cyclic acetal, right? So we'll protonate this alcohol group up here and make it a good leaving group. And then now this alcohol can attack that hemiacetal carbon and form a second ring, right? So now we formed this ring in the first step, this ring down here in the first step, and now we're forming this ring up here in these couple of steps down here. And of course, our last step is the deprotonation. So this H will just pop off the oxygen up top and leave us with this 2-ring system. Okay, and this is our last practice problem for acetals. All right, so hopefully the hint helped you a little bit. For a ring opening, the mechanism goes backwards, right? So for the ring closings or the ring formations that we saw earlier, the mechanism goes forwards, right? The PATED goes forwards. For a ring opening, the mechanism is just the reverse of that. So in order to solve this problem, we should think about PATED in reverse, right? So firstly, if we're thinking about PATED in reverse, we have the deprotonation step, right, which backwards would be a protonation. So we will protonate this oxygen first using some acid, right? And then if we think about our next thing, right, it's an elimination. So now we will try to eliminate this oxygen that we just protonated. We could do that by taking one of the lone pairs on this oxygen in this 6-membered ring up top and drop it down to this carbon, so the acetal carbon, and boot off the OH here. And that leaves us with this, right? Now this is a kind of poorly drawn molecule, so we'll just redraw this really quick. Notice that what was initially the acetal carbon is part of a 6-membered ring right here. So we will redraw that as our ring. And now using some water, we can attack this carbon right here and eliminate this this O. And that leaves us with this molecule right here. And then, of course, if we're attacking with water, we need to deprotonate that water. So our final step is a deprotonation, and we're just left with this.